world, but I think there's some nice graph theory here and some nice group theory, and hopefully you will enjoy the talk. So, and let me begin. So graphs on groups, I am going to mean, roughly speaking, graphs where the vertex set is the set of elements of a group G, and the edge morphism of G will be an automorphism of the graph. These are not going to be Cayley graphs. So for an example to show you the sort of thing we're talking about, the simplest and first example of this was the commuting graph of the group G, in which we put an edge from x to y if and only if xy equals yx. And this graph goes back to Brouwer and Fowler in their famous paper of 1955 on centralizers of involutions in simple groups of even order. So they proved that a given group can only occur as the centralizer of an involution in finitely many finite simple groups. Perhaps this was the first step towards the classification of finite simple groups. And one curious thing about this paper is that they don't actually use the term graph anywhere in the paper, but they define a distance function on the group where the distance between two elements is the number of steps that you have to take to get from one to the other, where each step the two ends should commute and they're not allowed to be the identity. So these are paths in the graph that you get by deleting the identity from the commuting graph of G. Okay, so the reason for that is that, of course, the identity and more generally elements in the center of the group are joined to everything. So if you're interested in connectedness, diameter, and questions like that, those questions all become trivial if you allow elements at the center in your graph, because you can get from anywhere to anywhere else in 2 steps by just going into the center. Leave the center in and take the whole of G to be the vertex set of the graph. And I'll call this commuting graph com of G, because there will be several other graphs coming up that need names as well. So that's the commuting graph. And here are 2 further graphs to give us something to think about. The power graph. In the power graph, you put an edge from x to y if one of x and y is a power of the other. And if you think about that definition, you see that it should really be a directed graph where you put an arc from x to y if y is a power of x. It's now more usually treated as an undirected graph, and that's what I'm going to do. And then related to that is the so-called enhanced power graph, where there's an edge joining x and y if x and y are both powers of some element z. So that would say that x and y both lie in the cyclic group generated by z, and therefore the group generated by x and y is itself cyclic. So that's another way of defining the enhanced power graph. And once you see that definition, you could say, well, you could vary it by taking some other property different from cyclic there. You could say abelian, for example. If you say join x and y if they generate an abelian group, of course you just get the commuting graph. And you notice that these graphs form a hierarchy. Each one, the edge set is contained in the next. So each is a spanning subgraph of the next. An edge in the power graph is clearly an edge in the enhanced power graph. And an edge in the enhanced power graph is an edge in the commuting graph because a cyclic group is abelian. And you could go on and say, well, what about joining x to y of x group generated by x and y is a soluble group? I will say something about that later on. The generating graph, which I'm not going to be talking about, you put an edge if x and y generate the group G. So there are a number of graphs like this, and I'm more interested in the relationships between these graphs than in the individual graphs themselves, though I will say something about the individual graphs. So there are three graphs which will do to get us thinking about the questions. So if we have a hierarchy like that, the natural first question is, what happens if two successive graphs in this sequence are equal? Which are the groups for which the power graph is equal to the enhanced power graph, and which are the groups for which the enhanced power graph is equal to the commuting graph? And the answers to both of those questions are known. The power graph is equal to the enhanced power graph if and only if every element of G has prime power order. That's essentially because if you had an element of non-prime power order, there would be some element of order PQ, where P and Q are different primes. Then the element of order P and the element of order Q generate a cyclic group, but neither of them is a power of the other. And so these groups, to tie up with what's coming later on in this session, these are precisely the groups for which the Grunberg-Kagel graph has no edges. The edges and the vertices of the Grunberg-Kagel graph are the prime divisors of the order of G, and you put an edge from P to Q if there is an element of order PQ in the group. But these are the groups that contain no such elements, so they're the groups for which the Grunberg-Kagel graph is the null graph. The enhanced power graph is equal to the commuting graph if and only if every Silov subgroup of G is cyclic or generalized quaternion. And the reason for that is that so what this would say is that whenever two elements commute, they generate a cyclic group. So in particular, the Silov subgroups, there are no subgroups CP cross CP, and so by an old theorem of Burnside, the Silov subgroups are either cyclic or generalized quaternion, and all these groups are classified as well. So we know we have complete lists of the groups satisfying either one of those conditions. And if you, the next question that you might ask, which I'm not going to be talking about, oh, I will a little bit, but you say, well, okay, for most groups, all these three graphs in the hierarchy are all different. So you could say, let's form a graph whose edges are the edges of the enhanced power graph, which are not edges of the power graph, or edges of the commuting graph, which are not edges of the enhanced power graph. I think there are some interesting questions about those. You could ask then about their connectedness, their connected components, their diameter, things like that. But very little's been done about that. But I'm going in a different direction. And this grew out of last summer, Ambat Vijay Kumar and Aparna Lakshmanan at Koshi in South India ran an online discussion group on graphs and groups, and quite a lot of the things that I've been doing grew out of discussions in that discussion group, and in particular what I'm talking about here is one of those, as you will see later. So, whoops, there they are. And one of the participants who gave a talk early on in this discussion group was Lavanya Selvaganesh, and she talked about what she called the superpower graph of a group. In the superpower graph, you join X and Y if there are elements X primed and Y primed having the same order as X and Y, which are joined in the power graph. So that was just a particular graph, and she was discussing that graph. But once you see that definition and you're thinking in terms of hierarchies of graphs, you say, well, that can all be generalized in the following way. So you have a graph defined on the group G, which might be the power graph. You have a partition defined of the elements of G, which might be by order or something like that. And we're going to build a graph using the same recipe that we just saw, but for an arbitrary graph on the group and an arbitrary partition of the group. So what we're going to say is The B super A graph on G has vertex set G. X is joined to Y if there exist elements X primed and Y primed, so that X primed is B equivalent to X, Y primed is B equivalent to Y, and X primed and Y primed are joined in the A graph, right? So if, for example, it's what we would now call the order superpower graph, you join X and Y if there are elements X primed and Y primed with the same orders as X and Y, which are joined in the power graph. So that's exactly Lavagna's definition of the superpower graph earlier on. So now we have, if you like, a two-dimensional hierarchy, because we can vary the graph through the hierarchy we just talked about. We can vary the partition into, well, there are various partitions that we might take. So, but there's another graph. You might say, well, every equivalence class, if you have two equivalence classes of B and you have one edge between them, then you have all possible edges between them. And it might be more sensible to contract that graph down so that each equivalence class becomes a single vertex. And I'm going to call that the condensed B super A graph. So the vertex set is the set of equivalence classes of the relation B, and you join two classes if they have representatives which are joined in the graph A. So in this first part of the talk, I will use just the B super A graph because I want to compare these different graphs. So I want them all to have the same vertex set. The vertex set in each of these graphs is G. But later on, I will do this shrinking down to equivalence classes and tell you about an interesting result that we got in that case. Okay, so if you have the condensed graph and you want to recover the original graph, you have to, as long as you know the sizes of the equivalence classes, you can just blow each vertex up into an equivalence class of the corresponding size, which will be a clique, and that will give the original graph. So these two things are going to have rather similar, some of their properties will be rather similar. So I've told you the three graphs I'm going to consider. Here are the three equivalence relations I'm going to consider. First of all, equality, which will just give us the original three graphs. Then conjugacy, and finally, same order. So we'll have the original graphs like the power graph, the conjugacy superpower graph, and the order superpower graph. Those will be some of the graphs we'll consider. So we'll have 9 graphs altogether. And as I say, you can imagine other equivalence relations, just as you can imagine other graphs. So I think there's a good stock of things here that have not been, questions that haven't been answered and haven't even really been looked at for the most part. So plenty to do. So as I said, with equality, we get the original graph A. So I'll talk about the conjugacy superpower graph like this, conj power of G, and the order superpower graph, ord power of G, similar notation for the other types. Right, so how do these graphs relate? So we get a two-dimensional hierarchy because we can increase the graph and we can increase the equivalence relation. And it looks like this. So the power graph is contained in the enhanced power graph is contained in the commuting graph. If you go to the conjugacy supergraph, you get those three. And if you go to the order supergraph, you get those three. So we have this two-dimensional hierarchy of graphs defined on a group. And I better prove something about them. Otherwise, you could say this is just generalization for its own sake. And I want to try to convince you of two things. Firstly, that they are closely connected to the graph structure. And secondly, there's some interesting mathematics that can be done investigating them. So those are my two aims in the rest of the talk. So the first thing I did when we produced this generalization, so let me just go back to the two-dimensional hierarchy. So there it is. You could say, well, we have 9 graphs there. Can we determine, for example, the classes of graphs for which any one of those is, the classes of groups for which any one of those is a complete graph? And here is the result. So this table describes groups where one of the 9 graphs in that picture is a complete graph. So the power graph is complete if and only if the group is cyclic. It is a cyclic P group, I'm sorry. Cyclic group of prime power order has the property that if you pick any 2 elements, one is a power of the other, and it's the only group that has that property. For the enhanced power graph, you require that the group is cyclic, and for the commuting graph, the group is abelian. So those things are all pretty obvious. Now, for the conjugacy superpower graph, it turns out that the classes are exactly the same. This is not a triviality. Essentially, what you need to prove that is an old theorem that goes back to Jordan in the 19th century, saying that if you have a proper subgroup of a group, then there is some conjugacy, a finite group, there is some conjugacy class which is disjoint from that subgroup. So we need that fact in order to prove that these are the same. When we go to order, things are a little different. For the order superpower graph, the answer is just a P group, because if you have any 2 elements of a P group, then you take the one of the larger order, the cyclic subgroup it generates contains an element of the smaller order, so those 2 get joined. For the enhanced power graph and the commuting graph, the answer is the same, and it is that if you let m be the exponent of g, there should be an element whose order is exactly m. So to put it another way, the spectrum of G, the set of orders of elements of G, is the set of all divisors of some number m. That characterizes when you get complete graphs in these 2 cases. Right. I have cheated you slightly. So if you go back to the last thing, those 2 entries are the same. Now, these 2 entries are the same for a slightly non-trivial reason. But these 2 entries are the same because the graphs are actually the same. For any finite group G, the order supercommuting graph and the order super-enhanced power graph coincide. That's not so difficult to prove. I won't give you a proof here. You can maybe take that as an exercise and try it for yourself. Those 2 graphs coincide. None of the other pairs coincide. So we actually have 8 graphs rather than 9 in this hierarchy. And one small question to which I don't know the answer is there a group for which all 8 graphs are different? For any given, if you take any pair of those graphs, I can give you a group where they don't coincide. I haven't really thought about this question, but it should be possible to find a group where all 8 graphs are different. But we do know something in the other cases. So you could ask the same question that we asked about the original hierarchy. When are 2 of the graphs in this picture? So if we go back to the picture again, here, take two of the graphs in this picture and ask, what can you say about groups for which those 2 graphs are equal? And of course, it would suffice to be able to deal with cases where the graphs are adjacent in this picture, because if we can tell when those 2 are equal and when those 2 are equal, then the conjunction of those conditions will tell us when those two are equal, for example. Right. So here is a theorem. When is the conjugacy supercommuting graph equal to the commuting graph? In other words, adding on this condition that you join the whole conjugacy classes when they contain elements that commute doesn't change the graph. That happens if and only if G is a two-angle group. That is, it satisfies the commutator identity x, y, y is equal to 0, where this repeated commutator means you take the commutator of x and y, and then you take the commutator of that with y. So the groups that come up putting those two equal are precisely the two-angle groups, which are a class that have had some amount of investigation. And the conjugacy superpower graph is equal to the power graph if and only if G is a Dedekind group, a group in which every subgroup is normal. So straight away out of the box, we get two rather interesting classes of groups there. Dedekind groups are all known. There's no mystery about Dedekind groups. They must be either abelian, so this groups with all subgroups normal, either abelian or of this form, A cross B cross C, where A is the quaternion group of order 8, B is an elementary abelian 2 group, and C is an abelian group of odd order. For angle groups, we don't have a complete determination, but we do know that they're sandwiched between the nilpotent groups of class 2 and the nilpotent groups of class 3. Nilpotent of class 2 means that the commutator identity x, y, z equals 1 is true for only x, y, and z, and so that's obviously stronger than the two-angle property. The two-angle property implies nilpotent of class 3. This was shown independently by Hopkins and Levy. So the angle result that I showed you before, so to go back, the groups for which the conjugacy supercommuting graph is equal to the commuting graph uses the following result. This is a characterization of groups satisfying the two-angle identity. I didn't know this before until we started doing this work. G satisfies the two-angle identity if and only if every centralizer is a normal subgroup. That's a cute little result. It should be classical, but the only proof we found was a stack exchange post by Korhonen, who used a published result of kappa. And if there was an earlier proof of this, I would be very interested to know about it. So please, if anyone knows an earlier proof of this characterization of the two-angle groups, I would like to know. Okay. So what about other pairs? So I'll leave you with the problem of taking that table of 9 graphs. Well, we know 2 of them are equal always, but in other cases, can you decide when 2 graphs are equal? For which class of groups is it the case that 2 of the graphs in that table are equal? So we've dealt with the equality between the unsupergraphs, the power graph, enhanced power graph, and commuting graph, and we've dealt with 2 cases in that theorem I just showed you, so there is still plenty to do. But as a generalization of deciding when the graph is complete, we could ask, well, what about dominant vertices joined to all others? Well, we saw that in the commuting graph, elements of the center are joined to all others because they are precisely the elements that commute with everything. So can we describe group theoretically the set of dominant vertices in these graphs in our two-dimensional hierarchy? Well, here are some results. We haven't completely finished this. The dominant vertices in the power graph, it's a little bit complicated. if G is a cyclic P group, it's the whole of G. G is a cyclic P group, then the graph is complete. So every vertex is dominant. If G is cyclic but not a P group, it's the identity. The identity is still joined to everything, but the generators of G are also joined to everything, because if you take a generator of G and any other element, they will generate a cyclic group. If G is a generalized quaternion group, then the dominant vertices are the two in the center, the identity and the unique non-identity central element. In all other groups, the dominant, only the identity is dominant. In the enhanced power graph, the set of dominant vertices is a subgroup of G that's made its appearance in various places, but it's not probably as well known as it might be. The cyclicizer of G. The cyclicizer of G, of course, by definition, we're looking at the set of dominant vertices in the enhanced power graph. So these are the group elements X, such that for any Y in the group X and Y generate a cyclic group. So it's a set of elements that generate a cyclic group with everything else in the group. And you can show that that is the product of the Celoff P subgroups of the center over those primes P for which the complete Celoff subgroups of G are either cyclic or generalized quaternion. So that's what it looks like. It's a subgroup of the center. And indeed, as the graph gets larger, the set of dominant vertices can't get smaller, so each must be contained in the next. And of course, the next one to appear is the commuting graph, and the set of dominant vertices in the commuting graph is just the center of G. So the cyclicizer is contained in the center, as it should be. Right, so there are the results for the original graphs, not including the equivalence relations. Can we say any more? Well, here is one result. If you take any of the three original graphs, the power graph, the enhanced power graph, or the commuting graph, and look for dominant vertices in the conjugacy supergraph, it's exactly the same as the set of dominant vertices in the original graph. And you may remember that when I showed you that table about when is the graph complete, in these cases here, the conjugacy supergraph was complete if and only if the original A graph was complete. And so this is a generalization of that. It says actually the sets of dominant vertices are the same. So if one is complete, that means every vertex is dominant, then the other one is also complete. So we have that. If G is not of prime power order and its exponent is M, then the set of dominant vertices in the order superpower graph consists of the identity and the elements of order M, if there are any elements of order M. If the order, this you remember was the condition for this graph to be complete, that there was an element of order M, so that every order of the orders of elements of G, the spectrum, are precisely the divisors of M. Well, in this case, if there are elements of order M, then they're dominant, but otherwise just the identity. So we know the answer in that case. So the remaining case would be the order supercommuting graph, because the other two graphs are equal. The order supercommuting graph is equal to the order super-enhanced power graph. So those two graphs are equal. So there's only one left to do. We don't know a good characterization of the dominant vertices in that graph. So now I want to move on to something a little different. Still okay for time. So, because it turns out that at least the condensed versions of some of these graphs have been looked at earlier, mostly not the ones I've been talking about. So this was for the conjugacy class equivalence relation. So you remember that we're now looking at graphs where the vertices are the conjugacy classes, and you join two classes C and D if there are elements in C and D which are adjacent in the original graph A. So that's the condensed conjugacy super A graph. And in the commuting graph, we joined X and Y if the group they generate is abelian. So people have looked at what happens if you replace abelian there by nilpotent or soluble. So which are the, what can you say about the graphs, or indeed the condensed graphs that you get by joining two conjugacy classes if there are elements in those classes that generate a nilpotent group or a soluble group? And as I say, these graphs have been studied before. And in particular, Herzog, Longobardi, and May looked at the commuting conjugacy class graph, which they called the CCC graph. So rather than make the name even longer, I will just use their notation. So the CCC graph is the commuting conjugacy class graph. So the vertices of the conjugacy classes, you join two conjugacy classes if there's an element in one and an element in the other which commute. And Mohammadian and Irfanian studied the nilpotent conjugacy class graph. So the natural next step would be the soluble conjugacy class graph. Join two conjugacy classes if there's an element in the first, an element in the second that generate a soluble group. So I'm going to tell you a little bit about this graph. So it's the condensed version of the conjugacy super graph for the for this soluble relation. And so these two authors, started work on this. They talked about it in the discussion group and invited me to join. I joined and we wrote a paper and put it on the archive. Benjamin Sambali saw it and suggested an improvement, so we invited him to join the team, and the current version of the paper on the archive is by the four of us. And I'm going to tell you a bit about this, and in particular, I will tell you about one of the main theorems that we proved. So first of all, when is this graph complete? Well, there's an old result going back to Landau in 1903, which states that there are only a finite number of finite groups with a given number of conjugacy classes. If you want a group with just 3 conjugacy classes or 190 conjugacy classes or any number you prescribe, there will be only finitely many groups that will have that many conjugacy classes. And the proof is probably well known. It's, for example, it's an appendix in Burnside's group theory book from 1911. If G is a soluble group, then any two elements generate a soluble group, so the soluble graph is complete. And the converse is also true. This follows from Thompson's classification of N groups. So N groups include the minimal simple groups. And so if you have a group in which any two elements, or any N group is 2 generated. So if you have a group in which any two elements generate a soluble group, then the group can't contain a minimal simple group, can't involve a minimal simple group, and therefore it must be a soluble group. And in fact, that result has been generalized. So this says a group is soluble if and only if any two elements generate a soluble group. But Dolphy, Guralnik, Herzog, and Prager generalized this result. They showed that if given any two conjugacy classes, there are elements in those classes that generate a soluble group, then G must be soluble. So in other words, the soluble conjugacy class graph of a group is complete if and only if the group is soluble. That follows from this result of Dolphy, Guralnik, Herzog, and Prager. Right, so we know when they're complete. And if we combine that with Landau's result, we see, this seems a slightly odd way of putting it, but you'll see, excuse me, you'll see why I put it in this way in a moment. So, there are only finitely many finite soluble groups whose SCC graph has given clique number, because if you have a soluble group, then this graph is complete, and therefore to say you're specifying clique number says you're specifying the number of vertices, which is the number of conjugacy classes, and according to Landau, there are only finitely many such groups. So that we have that slightly odd-looking result, but we were able to generalize that. Given a positive integer d, there are only finitely many finite groups for which the clique number of the SCC graph is equal to d. In other words, so in a sense, this is a generalization of Landau's theorem, if you want to put it that way. It says that if you look at the conjugacy classes and you join two of them, if they contain elements generating a soluble group, you look at the clique number of that, then there are only a finite number of finite groups where that clique number is given, is the number d that you specified. So in particular, if you ask that the clique number of the graph is at most 3, then you have only 4 groups, the cyclic groups of order 1, 2, and 3, and the symmetric group of degree 6. They're all soluble groups, so in each case, the graph is complete on 1 vertex, 2 vertices, 3 vertices, and 3 vertices in this case, because the symmetric group of degree, of order 6, of degree 3, beg your pardon, can you, if you're taking notes, can you please change that? It's S3, degree 6. It has 3 conjugacy classes, and so it's a complete graph on 3 vertices. And we haven't examined the growth rate of this function. So the function would be the number of groups or the largest order of such a group. And we haven't even tried to extend this result from clique number 4 to clique number 3 to clique number 4. You notice that if you take the alternating group A5, has 5 conjugacy classes, but the clique number is 4 rather than 5, because you cannot find an element of order 3 and an element of order 5 that generate a soluble group. So it's K5 with 1 missing edge. Okay, so I'll give you a sketch of the proof. You can probably guess roughly how this proof will go. So we can assume that G is not a soluble group, and then so we look at the soluble radical, and we show that you can factor it out essentially, and you can assume that the soluble radical is trivial. What I'm saying is that if you can show that there are only finitely many groups with trivial soluble radical satisfying our condition, then there are only finitely many groups altogether. And then you can further reduce that to the case where the socle is almost simple, and then you can invoke the classification of finite simple groups, and it's not a terribly long search through the list of finite simple groups to find the result. But in fact, there's another way to proceed for the last bit of this argument, which I'd like to tell you about. So once we know that the group is simple, we can argue like this. The clique number of the soluble conjugacy class graph is bounded, then the number of prime divisors of an element order is also bounded, because you see, if you have an element divisible by d primes, then there are 2 to the d, at least 2 to the d divisors of that element, and they will form a complete graph in the complete subgraph of the SCC graph. Now, there's a recent result of Hung and Yang that bounds the number of prime divisors of that group in terms of the number of prime divisors of the element order. And once you've bounded the number of prime divisors, you can actually bound the orders of these prime divisors recursively, and in which case we have a bound on the exponent of the group. And it's an old result that goes back to Gareth Jones in 1970 or so, that there are only finitely many finite simple groups with given exponent. Of course, 1970 is pre-classification. He proved it for the then known simple groups, and the ones discovered since then do not affect the truth of this result. So that was the argument that Benjamin originally suggested, that you can do it directly by just looking within the finite simple groups to see what sort of clique size you can have. So that's probably our biggest theorem. Right, well, I have one more topic that I want to tell you about, and let me introduce it in the following way. Suppose we have some kind of graph on a group. I don't care what kind, but I want to know, are those graphs universal in the sense that every finite graph can be embedded as an induced subgraph in A of G for some group G? In other words, you give me a graph, I can find a group for which your graph is embedded as an induced subgraph in A of G. And remember that an induced subgraph means I use a set of vertices and all of the edges of the graph that are contained within that set. So what can we say about universality of some of these classes? Well, I'll tell you a little bit about that. The power graph and its two supergraphs are not universal because they are all comparability graphs of partial orders. In other words, in each case, there's a partial order such that two elements are joined in the graph if and only if they're comparable in the partial order. And this is a restricted class of graphs. Not every graph is the comparability graph of a partial order. So in particular, comparability graphs of partial orders are a famous class of perfect graphs. Perfect graphs, according to the strong perfect graph theorem, are precisely the graphs that don't contain odd cycles of length greater than 3 or complements of such cycles as induced subgraphs. So, for example, the 5 cycle cannot be an induced subgraph of a power graph or a superpower graph. So the answer for power graphs is not everything, but the enhanced power graph and the commuting graph are both universal. In fact, you can prove they're universal in a single argument, which also does something else. And I want to tell you about that because I think this raises many interesting questions about graphs on groups, which some of you might like to tackle. So here's a theorem. So I'm not just taking a graph and trying to embed it. I'm taking a complete graph with 3 colors of edges, let's say red, green, and blue. So embedding a graph as an induced subgraph would like be taking a complete graph with 2 colors, 1 color for edges and 1 for non-edges, and embedding that. But we can do 3. If you color the edges of a finite complete graph in any way, red, green, and blue, I can find a group G so that the red edges belong to the enhanced power graph, the green edges belong to the commuting graph, but not the enhanced power graph, and the blue edges are not in the commuting graph. So we can do all of that in a single group G. And so as a consequence of that theorem, you see that enhanced power graphs are universal, because if you forget about the difference between green and blue, just look at the red edges. They're the ones that go into the enhanced power graph. The commuting graphs are universal. If you identify red and green, then those edges belong to the commuting graph. But also, if you look at, I mentioned briefly that there are interesting questions about the differences between these graphs. If you look at the difference between the commuting graph and the enhanced power graph, that is, the graph whose edges are pairs that commute but don't generate a cyclic group, then those graphs are also universal, because if I forget about the distinction between red and blue, the green edges are the ones that belong to that difference, and the red and blue edges don't. So we get, from this single theorem, we get 3 universality results. I would like to see more theorems of the same sort. But anyway, there's something. And so I started wondering, well, we've got these SCC graphs. Are they universal? Is it true that every finite graph can be embedded in the SCC graph of some finite group? I do not know. And in fact, what I'm going to show you is, well, it's an example of a really very weak-looking theorem whose proof uses some really rather deep mathematics. And it's curious that should happen. It makes me wonder what's going on, but I really do not think that what I'm telling you is best possible. So up to you to try and find an improvement if you would like to do that. So I'm going to embed graphs in a very special class into the SCC graphs of finite groups. And the graphs that I'm going to embed will be the so-called threshold graphs. A threshold graph can be defined in a number of ways, but the easiest way to describe it is to say that for each vertex x, you have a weight, a real number weight, w of x. And there's also a threshold t. And you join x and y if the sum of their weights is greater than t. Since we're dealing with finite graphs, you can assume that t is not ever equal to the sum of 2 weights. So you can assume that for any 2 vertices, either the sum of the weights is greater than t and you join them by an edge, or the sum of the weights is less than t and you don't join them. So that's a threshold graph, and they've made various appearances in graph theory in various places. And indeed, they can be defined by forbidden induced subgraphs. There are 3 forbidden induced subgraphs on 4 vertices: the cycle, the path, or 2 disjoint edges. And I can explain fairly easily why this is true. Suppose, let's just look at the cycle for a moment. The argument's exactly the same for the other 2. In the cycle, you can take 2 opposite edges of the cycle. Because they're opposite edges, the sum of the weights at the first edge is greater than t, the sum of the weights at the second edge is greater than t, so the sum of the 4 weights is greater than 2t. But on the other hand, if you look at the 2 diagonals of the cycle, they're non-edges. So the sum of the weights on the first diagonal is less than t, the sum of the weights on the second diagonal is less than t, and so the sum of the 4 weights is less than 2t, and that's a contradiction. So these are precisely the 3 graphs on 4 vertices that don't contain both 2 disjoint edges and 2 disjoint non-edges. And so the same argument deals with all 3. So these are the threshold graphs. And you can also describe them by this building up procedure. You start off and add vertices in one at a time. Each new vertex is joined to either all or none of the existing vertices. You can show that this construction builds all threshold graphs. Anyway, those are the threshold graphs, and we're going to show that SCC graphs of finite groups at least embed all threshold graphs. So for any threshold graph, gamma, there is a finite group G such that the SCC graph of G contains gamma as an induced subgraph. And as I say, it's unlikely to be best possible. I don't know any graph that can't be embedded in the threshold, in the SCC graph of a finite group, but this is all that I can actually prove. And so here's the real embarrassment. To prove this rather weak-looking result, I need the famous theorem of Green and Tau about primes in arithmetic progression. So, you know, one of the more spectacular recent results in number theory. Let me at least give you a rough sketch of the proof. But before I do, let's just observe that this theorem is certainly not best possible. if you take the group S7 and take the following conjugacy classes: a 7 cycle, 2 disjoint 3 cycles, a 4 cycle, and a 5 cycle. In that order, we have a path in the SCC graph, because the 7 cycle will be normalized by some element which is 2 disjoint 3 cycles. Given 2 disjoint 3 cycles, we can take a 4 cycle which contains one of the 3 cycles and the fixed point, and the group they generate will be something like will be S4 will be C3 cross S4. The 4 cycle and the 5 cycle, we can take the 4 cycle to normalize the 5 cycle, so we get a path like that, and there are no other edges, because you can see that a 7 cycle together with either a 4 cycle or 5 cycle generates an insoluble group, and similarly 2 disjoint 3 cycles and a 5 cycle. So anyway, so roughly how does the proof go? Here's a sketch. Given a threshold graph, vertex weights and threshold. Now, there's quite a bit of flexibility in the definition of a threshold graph. As I said, you can assume that there isn't any edge where the sum of the weights is precisely equal to the threshold. That means you can move the threshold around in an interval. You can also adjust the weights a little bit, as long as you don't cross over the threshold. So there's quite a bit of freedom. In particular, you can adjust the weights to make them rational, and you can multiply up to make them integers, and then you can scale up those integers and scale and shift them so that they're primes in an arithmetic progression. You see, if they're integers, they belong to an arithmetic progression of difference 1. And if we can scale them up, we can make an arithmetic progression of arbitrary difference. And if we can shift them, we can make them agree with one of these Green and Tau arithmetic progressions of primes. And now we can assume the threshold is greater than all the weights. So you can take the symmetric group whose degree is the threshold and take the vertices to be conjugacy classes of cycles of the appropriate prime length. Now, if the sum of 2 of those primes is below the threshold, you can find disjoint cycles. They will commute, and so they will generate an abelian group. If the sum of the weights is above the threshold, the supports will intersect, and the prime cycles will generate the alternating group on their support, which will not be soluble, because we're talking big primes here. So that gives you the given graph as a, well, actually it gives you the complement of the given graph, because if the sum of the weights is below the threshold, then we've got an abelian group. If it's above, we've got an alternating group. So you have to complement the graph before you do this. So anyway, that's a sketch of the proof. And as I say, it's surely not best possible. And I think the way to prove that would be to say, well, we've got so much freedom in adjusting these weights that we ought to be able to take a more general kind of graph and use primes in this way. I mean, this seems like a good way to generate a group with a given graph embedded as in the SCC graph, but we have to be able to build that from an arbitrary starting graph. So that's a sketch of the proof. So I'm coming to the end. Here are some references, and I'll come back to this page in a moment, but let me just say, I'll stay on this page, why not? Let me just say thank you for your attention. There's the, how did that happen?
Thank you so much for the outstanding talk with many new concepts and ideas. Are there any questions or comments?
Can I ask a question?
Yes, sure.
Yes, please do.
About Euler's theorem.
Yes.
It seems to be very, very similar to concept of Greenberg-Kegel graphs of symmetry and alternating groups.
Very much so, yes.
Is it
Indeed.
true? The adjacency criterion for Greenberg-Kegel graphs are very similar.
Yes, if you just restrict to cycles of prime order, then it's very similar. It's not quite the same. I haven't really looked at what the relationship is, but I'm sure there are similarities there. And perhaps, Natalia, you're the person to sort that out.
Thank you.
I'm sure there is something there, and maybe we should think about that. Might be a nice project.
Possibly, yes. It's a good idea. I have some ideas how to continue. And,
excellent, excellent.
I have asked you in email to send me your slides. Could you please send?
Yes, I will send you your slides, my slides,
Thank
sure.
you.
Right away. I can't do it right now because I now have to take Rosemary up to the hospital for her physiotherapy. But when I come back, I will send the slides off.
Thank you.
Thank you. And are there any other questions or comments? If no, maybe I have one maybe stupid question.
Yes, please. Please.
As I understand, the results on supergraphs are about supergraphs constructed on the set of equivalence classes. Yes.
Yes.
About how to say about the contracted form. Yes.
Yeah. For the contracted form, you just use the equivalence classes as vertices. Yes.
But
yes.
Is it interesting to study supergraphs constructed on the set of elements of our group? Maybe they are quite complicated.
Well, that's what we started doing initially. So this paper, this first paper on this list here, just deals with the elements, the graphs defined on the elements of the group. So you might like to look at that first. So that's what we were doing. The reason for doing that for us was that we wanted to compare these graphs, and so we want them all to have the same vertex set. But you see, if you go to the supergraph, each equivalence class will be a complete graph, and any two equivalence classes will either have no edges or all possible edges between them. So the very natural thing to do is to shrink them down to single vertices and use the condensed graph. And that's what we do in the second paper here. So I think both things are interesting, but it depends which question you're trying to look at. So, for example, if you want to know the size of the largest complete subgraph, you might look in the condensed graph and then just blow it up to a complete subgraph by going back to the original.
Yeah, thank you. I understand a little bit. Any other questions or comments? And if no, let us thank Professor Cameron again